All right. Chapter 10, assignment 2. Here we go. First question is about who owns iPods. Those were all the rage when I was about 20 years old. Um, as part of a new part of the Pew Internet and American Life Project, researchers survey a random sample of 800 teenagers and a separate random sample of 400 young adults. For the teens, 79% said they own an iPod or an MP3 player. For the young adults, this figure was 67%. Is there a significant difference between the population proportions? State the appropriate hypotheses for a significance test to answer the question and define any parameters. So let's start with the parameters. I would say maybe P T would be the proportion of teens who own an iPod slash MP3 player. Then I'll just copy this and paste it again and just tweak it because the next one is pretty much the same thing. It's just going to be the proportion of young adults. So let's just swap that subscript out for a Y and replace teens with young adults who own an iPod or an MP3 player. So those are the two. So the null proportion is always that these two proportions are equal. So proportion of teens equals proportion of young adults. Or you could also do the null could be that PT minus PY young adults is 0. If they're equal, when you subtract them, you would get nothing. The alternative is that they have a difference. So that would just be PT is not equal to P sub Y. Or again, if you write it as a subtraction, that if they're not the same, when you subtract them, you will not get 0. So this would be a two-sided test, by the way. Okay. Number 17 is just to go ahead and carry out the whole test. So that's HYTAPSY. So the HY we already did right there. The T, remember T is for the test. This is a two-sample proportion z-test. That's what we call this, okay? Then the A is check the 3 conditions. So number 1, was it random? I'm pretty sure it's set up here in the directions. A random sample and a random sample, so you could just say that it was stated. Number 2, is it approximately normal? Do we have 10 successes and failures in each group? Well, we have 800 teenagers and 400 young adults. And they give us the percentages. So the teenagers were at a 79% clip. So I should do some quick math here. I can tell those numbers are pretty big. So 800 was my teenagers, and 79% of them had an iPod. So that number is 632. If I do 800 minus that, I've got 168 teenagers that did not own one. So those are both greater than 10, but also do the same thing for the young adults. That sample size was less, that was 400 right here. And in that sample, if you keep reading for young adults, 67% was their proportion. So 268 had an iPad. Those were the successes. 400 minus 268 is the kids that don't. So both of those are good. So it's approximately normal. And number 3, is it independent? Well, do both of them Are 800 teenagers less than 10% of all teenagers? Yeah, eight. So if I do the 10N rule, that's 8,000. Is that less than the population of teens? Yes. Is 400 young adults times 10, that's 4,000. Is that number less than the population of young adults? Presumably, it's not even close. So, I'm good. I did my H, did my T, did my A. Got to find the p-value. So at this point, if this were an FRQ, I'm going to switch colors. I don't like writing in red, but I did anyway. At this point, you are going to show the formula for your z-score. You're going to show me what you would actually be calculating, but then use the calculator to do it, okay? So remember, you're going to subtract the two proportions on the numerator. So 0.79 minus 0.67. That, again, is going to be my, if I was doing a point estimate, that would be it. I'm not making an interval, but that would be my point estimate. Minus 0. Remember, where does that 0 come from? That 0 is the null. So we believe the difference is going to be 0. And then I divide by, here's the crazy part, that big square root formula, okay, where you have to do essentially the standard deviation for the teenagers plus the standard deviation for the young adults. But before I do that, I have to pool the two groups together um, when I do the denominator. So this is called PC, sometimes is what it's called, or maybe you'll see it as P combined. I need to do, let's see, what was it for the teenagers? It was 632 out of 800, but I'm adding that to the young adults. If you need a little help, that came from that number right there. That's how many successes I had for teens. For the young adults, there were 400, and I had 268 successes. That's this number right here. You are combining them because we're testing this, okay? So we don't want to use these separately. We want to combine them to have a more averaged out combined P. I wrote this down somewhere. Oh, that's actually pretty easy. That's 900 out of 1200. So that's 0.75. That is what I'm going to use in here, okay, for both of these pieces. So the first piece, I'm dividing by 800. So this is like my teenager standard deviation. And then I'm going to do it again, 0.75, 0.25. And this part is for the young adults, so I divide by 400. But again, you have to do P combined here, well, here and here, okay, to do that. Now, at this point, I would call this good. I have done enough. I have showed the formula. If you want to try to do that by hand, go for it. I'm not. I'm going to use the calculator. So it is stat tests. It is a two proportion z test. So that is number 6. And then we enter in all those numbers. We had 632 out of 800 for the teenagers, and we had 268 out of 400 for the young adults. It is a not equal to, so you can see that there, and I will go ahead and calculate it. Okay, so my z-score is 4.5. That's huge. And my p-value, you can see there, you might think it's about 6, but be careful, see the scientific notation, E negative 6, meaning that it's practically 0. So 4.5, let's round that to 3. Okay, that is my test statistic, right? Test statistic. And my p-value is, well, it was like 6.0. It was practically nothing. What was it again? 6.03, that's what it was, times 10 to the negative 6, which is point, count them with me, 1, 2, 3, 4, 5 zeros before 603. So for all practical purposes, it is nothing. So now we can make our conclusion, okay? With P way less than alpha, I don't even know what alpha is, but it's way less than any reasonable alpha, we will reject the null. So we are rejecting this, that we're rejecting that they're equal, so this is gone. The evidence is significant. It supports the alternative that the two proportions are not equal. Okay? There is convincing evidence that the proportion of teens and young adults who own an iPod, sorry, are not the same, are different. Which makes sense. You know, even a 10-year gap from teenagers to young adults, that iPod phase was brief, folks. Okay, so that was a full test there. 21. This is a large clinical trial. They gave women a new diet to see if what effect it had on breast cancer. They gave them a normal diet or a low-fat diet. You can see a normal diet or a low-fat diet. So to check that the random assignment did produce comparable groups, we can compare the two groups at the start of the study. Ask if there's a family history of breast cancer, and then there's the results. 3,396 of the 19,000, these are big numbers. There's women in the low-fat diet, and then there's women in the control group. The control group got, I'm assuming they got the normal diet, okay? If the random assignment worked well, there should not be a significant difference in the proportions of family history of breast cancer. So, there we have it. All right. How significant is the observed difference? Part A, carry out an appropriate test. All right. Sounds like, to me, that we're doing a full test again, a full high TAPSE. So, let's define what we have here. What subscripts do I want to know? Maybe PN is the proportion of women with, let's just say, family history I'll write the whole thing, of breast cancer on the normal diet. And again, I don't want to write that twice, so I'm going to copy this and paste it right underneath and change a couple things. So, and then it will be, let's do P, maybe LF. So remember, the only difference is that some women had a normal diet, some people had a low-fat diet. So, PN and PLF, okay? The null, as always, is that these two things are the same. So if you were to subtract them, PN minus PLF, you get 0. The alternative would be that it just says that there should not be a difference. Okay, so if we subtracted them, it's not leading you to a less than or a greater than sign. It just says not different. Okay, so those are them. Name the test. two sample proportion z-test. Okay. Conditions. Number one, random. It was. It says up here um, that random assignment. So they were randomly assigned to either group. So check. Number two, large counts. I mean, look at these numbers. They're all in the thousands. 3,000 here, 4,000 here, 19,000. So you could take your time and dig into it, and you probably should. So, so we had 3,396 right here. You should calculate how many is the complement of that number. So what's 19,541 minus 3,093,396. So you get 16,145. Similarly, with the other group, with the low-fat diet, we had 4,929 that that said yes, so successes, so to speak. 29,294 minus that number, 4,929, is the number of women that said no. Okay, all of these numbers are far greater than 10. So we're good, so it's approximately normal. Lastly, independence. Maybe you could just say one woman's family history of breast cancer is separate of another. I'll just say that. One woman's family history is separate of another, is independent of another. All right. Then we'll get into the Z formula. We should do a little bit more background work first. What is Pn? That is 3,396 over that big number, 19,541. And you get about 0.174 if you divide those. And if you do the proportion for the low-fat diet, you get 49.29 out of 29,000. I'm just trying to slow down, make sure I get the right numbers. And that proportion is 0.168. Okay, we also need to find the PC, the combined proportion for both groups. So yes, these numbers are a little large and kind of annoying. I get that. So the denominator, you're adding up the two sample sizes. The numerator, you're adding up the number of women that said yes. Okay, very kind of annoying, but so we had 8,325 women on the numerator that said yes. The two sample sizes combined is over 48,000 women. But this gives you a more reasonable middle averaged proportion that we can use for the test. So it's about 17%. All right, whew, that's what we need now. So Z score is, we're doing, which way were we subtracting? We are doing the normal diet minus the low-fat diet. So this is 0.174 minus 0.168 minus 0, because remember the null is 0. Oftentimes, if you've done this a few times, you just start leaving this off because you know it doesn't do anything. And then the denominator is the crazy massive standard deviation thing. But you're going to use 0.17 and 0.83 because that's 1 minus 0.17 for both of these. And the sample sizes of each. So this would be the normal diet. This one that I'm writing now would be the low-fat diet. This is a massive study, 48,000 women. Hoofda. And at this point, I would ditch this and be like, okay, calculator, help me out. Stat tests. Where was I? Number 6. And type in these numbers very, very carefully. So 3,396 out of 19, 541. The low-fat diet was 49.29 out of 29, 294. Boop. And there you go. So there's your z-score is 1.59. And my p-value is 0.111, it looks like. Okay. There you go. Okay. And so with p greater than alpha, okay, we have, I think alpha was given to you up here as 0.05, if I remember right. Maybe I made that up. Well, if it wasn't given to you, we go with 0.05. Okay. We will fail to reject the null. Okay. The evidence does not support the alternative, does not support there being a difference in these proportions. Hoofda. Okay, I just realized I've left myself no space for the follow-up, part B. So maybe I'll just talk you through it. Describe a type 1 and type 2 error in this setting, okay? Type 1 is when you reject this, but it's true. So type 1 would be when you're claiming, if you reject this, you're claiming this is true. You would claim there is a difference, but in reality there is not, okay, between these two groups. A type 2 error is when you reject this, but it's true. You say there is no difference between these two diets, okay? But in reality, there is a difference between the two diets, okay? So then the question is, well, which one is more serious? A type 2 error would be more serious because the experiment would proceed assuming that the two groups were similar to begin with, and any conclusions that they make about the differences between the two groups at the end of the study would then be suspect. So there you have it there. Moving on. Multiple choice. I love multiple choice. This is a sample survey of 500 female students in college and 550 male students. They were each asked if they had a summer job last summer. Okay, 410 women said yes, and 484 men said yes. Okay, what are we testing here? And it says we conjecture before seeing the data that men are more likely to work. Okay, so that one would be, which one is more likely? Well, first of all, folks, look at this. It's never this and never this. The null is always equal to 0, so you can get rid of D and E right away. So, okay. And then it says we're doing males minus females, right? Every time, M minus F every time. And it says men are more likely to work. I figured out the two proportions to help us. The males were at 88% and the females were at 82. So the evidence for the alternative would be 88 minus 82, which is 0.06, which is greater than 0. So it's this one. C, they want you to just find the pooled sample proportion, which we've been doing. So like this first part, this here would be the males, and that's these numbers right here. And the second part, X2 and N2, would be the females, which is that part right there. So you just add them up and combine them. So all total, it looks like we had 894 that had a job out of 1,050. And when you divide those, let's see, if I get this right here, that is going to be B. It's going to be, no, sorry, that's going to be D. It's going to be 80, about 85%. Okay. 31. What is the confidence interval for this? Okay. Well, first of all, I can rule these out, right? Because I already did 0.88 minus 0.82 to get the difference. So I know it's a positive difference. So I know the point estimate's going to be A, B, or C. Ooh, see how they show this. They have the point estimate, and then this number here would be the margin of error. Okay, let me have my calculator give me the interval. Okay, stat tests. This is the interval button, so it's not number 6. This is the capital B button. I gotta get those numbers in there. Hold on a second. So we had, sorry, this is kind of slow. So we had 484 out of 550 for the males, 484 out of 550. For the females, we had 410 out of 500. Sorry, split screen doesn't work so well when I'm on the internet calculator. So, and then I'm gonna, ooh, did it give us the confidence rate? It did not, did it? So I'm gonna do 95%. Oh, it did. I'm sorry, right there. So 95%. Hit calculate. There we go. So it goes from 0.016 to 0.103. That's the interval. Okay. So 0.016 to bad memory fag, holy cow, 103. I like to do this, draw my interval on a number line. I know that I've got 0.016 down here. I know the middle is 0.06, and I know the high point, the high mark is 0.103. The margin of error, folks, is like how long is this each of these green sections? That's the margin of error. So I like to simply take I like to take this minus this. That's the way my brain sees it. You could also do 0.06 minus 0.016. I'll do both. You'll see that they're the same. So that's 0.043. If I do 0.06 minus the lower boundary, I get this pretty much the same thing. Again, those are because it's been rounded. Notice that rounding, either way, it's going to lead you to this one, you guys. So the answer is B, because that's not the margin of error, and that's not the margin of error. This is 0.043 on both sides of this. Okay, last one. 32 in an experiment with rats. Ugh. They're testing the memory of rats to learn whether substance M, whatever that is, can help restore their memory. They treated 20 rats to, okay, the brains of 20 rats were treated to damage their memories. The rats were trained to run a maze. Sounds kind of inhumane. After a day, 10 rats determined at random were given M, and 7 of them succeeded in the maze. Okay? And only 2 of the 10 rats in the control group. So we have 7 out of 10, and the ones that were given the substance, so it helped them remember. and only 2 of the 10 in the control group were successful. Then it says, we go on, the two samples z-test for no difference against a significantly higher proportion of the M group succeeds. Okay. What is it going to do? Is it going to give A, B, C, D, or E? Well, this one might be kind of strange. So what you're essentially going to be able to do is you can do the test button to get your z-score and see if it's one of these three. But you should also look into D and E first. The sample z-test should not be used because the random condition is violated. Was the random condition violated? I don't think so because it says determined at random. So it was random. Okay. What about E? The test should not be used because the normal condition is violated. In this case, normal condition is large counts. Oh, I think we're getting somewhere. Did we have 10 successes and 10 failures? No, not at all. In fact, I don't think any of them were. We had 7 and 3 in the green group. 7 succeeded, 3 failed. In the red group, 2 succeeded and 8 failed. These are all less than 10. So this is the one, folks. It is not normal. I do want to point out, though, if you took out your calculator and you did the two sample z-test, it's going to lead you to one of these, and it's like a distraction. If you do test and do number 6, two proportion z-test, you have your two groups are 7 out of 10 rats and 2 out of 10 rats. And there's your results, right? And it's the not equal to one that I have selected, okay? Your z-score is 2.25, so it's one of these. You're like, okay, so maybe you're eliminating B. But then what's the p-value? 0.024. That's actually this, right? Because isn't 0.024 in between 0.02 and 0.04? So anyway, my whole point with this is you might be misled and you might be like, there it is, it's C, because you haven't checked the conditions, okay? You should always check the conditions. So it's not C, it's E. All right, that's it.